Welcome to the Maguire Iron Podcast. My name is Brian Cooper. I am the Director of Marketing at Maguire Iron and your host for this podcast. At Maguire Iron, we have been helping to store and protect quality water for over 100 years. On today's show, we will discuss zinc-rich primers and how they are used in the water tank industry. To understand more about this metal and how it's used in coatings, I'm joined by two industry experts, Jamie Mays, the Director of Sales for Maguire Iron, who is also a NACE Level 3 inspector with over 25 years of experience in the water industry, and Eric Zimmerman. Eric is a project development manager for Sherwin-Williams and has been at Sherwin-Williams for over 20 years. Eric, give our listeners a little bit about your background.
Well, I'm responsible for the water business for Northwestern North America, and my job is to work with large municipal owners, specifying engineers, and contractors to help drive our water business in multiple segments: water storage, transmission, treatment, wastewater treatment, and then sewer collection as well. Those are the 5 subsegments that we break the water market up into. So I'm responsible for growing that business through North America.
I'm going to talk a little bit today about zinc primers. First of all, what is a zinc primer?
Well, a zinc primer is a corrosion inhibiting product that's a heavy metal filled product that acts as a primer, where zinc, when you look at the galvanic series, is a less noble or more active metal than what carbon steel is. So it gives itself up, it sacrifices itself to protect the host carbon steel substrate, acts as a cathode. And zinc primers come in several different levels. If you look at SSPC, or the Society of Protective Coatings, they classify zinc primers in 2 types. Type 1 are inorganic zinc primers. Type 2 are organic zinc primers. And they have 3 different levels, and the levels are associated with the percentage of zinc that's in the dried film. Level 3 is 65 to 77%. Level 2 is up to 85%. And then level 1 is any zinc-rich primer that is above 85% zinc in the dry film content.
So when was zinc developed, or when did somebody figure out that zinc could be used to theoretically protect metal?
Well, the first known case histories of using zinc as a cathode was the British Navy in the early 1800s. They put them on the outside of their copper ships, but they quickly found that the copper fouled and it decreased the speed of the ships. And so they had to make a hard decision to protect their ships from rusting or slow them down in battle. So the British decided that they would have fast ships that they replaced because of corrosion issues. But as a coating, the first zinc-rich coatings were applied in the 1930s. And those formulations existed until the mid-60s, when the advancements in inorganic zincs really came into play. And those are some of the technologies that we still participate with today.
So where is zinc used today? You talked about where it came from being used on ships. Where all is it used in the industry today?
Well, I mean, it's still used quite significantly in the marine industry, where they will actually place zinc ingots on the side of ships for cathodic protection. It's used quite frequently in the bridge industry, in high dollar infrastructure, structural steel of stadiums, and high dollar commercial structural steel applications. And then for our purposes in the water industry, it's used very commonly as an interior and exterior primer for water storage tanks.
So there are also, you use them on water storage tanks, as you talked about, bridges, different kinds of construction. there are also different kinds of zinc primers. Talk about that a little bit, because I think it's important to talk a little bit about the differences and how they're used and why they're used that way.
Well, and I alluded to that earlier. Type 1 for SSPC Paint 20, Type 1 zinc-rich primers are inorganic zinc primers. And those primers, their binder resins are inorganic in nature. Typically, they're ethyl silicate backbones, and they cure using the residual moisture that's in the air. And those primers offer some significant benefits. They offer much higher heat resistance, much better corrosion resistance for the most part. And part of that is because of their curing mechanism, they must go to a much more stringently applied steel surface. It has to be near white metal blast, and it has to have good angular profile and cured and dried in a controlled environment. So therefore, they're excellent for shop fabrication applications, and they're great for high heat applications, but they don't apply so well in the field. For field applications, you have the Type 2 products, which are organic zinc. And basically what that means is their binder resin contains carbon. And so you will have either a urethane with a moisture cure urethane backbone, or an epoxy zinc-rich primer that contains carbon. And it has some benefits on the application side, where it can go to less stringently prepared substrates, an SSPC SP6. These can be applied in immersion service in many applications, and it has a wider parameter of atmospheric conditions that it can be successfully applied to, especially with moisture cure urethanes, where you can have very low temperatures, very high humidity, and still form a film.
So this is a great spot. We also have Jamie Mays, who is the Director of Sales at Maguire Iron and also an ACE 3 inspector, joining us as well. And this is a great place to bring you in, Jamie, because you have a lot of knowledge in the water industry, and there is a back and forth when we talk about zinc primers and really what they do and are they really beneficial. From your experience, talk a little bit about your experience with zinc primers.
I'm always curious whether or not the zinc, because it's encapsulated inside a resin, if it truly does have these sacrificial properties, and whether it just not, as the lamulates lay across, whether the moisture actually works its way through the coating and just creates a 2 mil coating and makes it act like a 6 mil coating, or if it truly does sacrificial, because we still see isolated corrosion under a zinc-rich primer. And so that leads me to question whether or not it's truly acting as a cathode in that situation.
Or a barrier coating. Yeah, right.
Or a barrier
exactly.
coating, right? We know it's a barrier coating. It does it expand from a 2 mil to almost acting like a 10 mil because the moisture travels through that coating. So that was my only biggest concern about it. As a shop application, I love how fast it dries. I love the way it sprays. And so there's a lot of great applications that way from the past where we had slow drying primers. So just curious as to whether or not you feel that the resin itself encapsulating the zinc truly is still allows it to be a cathode.
I think there's some significant debate about that. You can read numerous industry papers that argue both sides of that. I do think that there is some corrosion benefit gained from a zinc primer, but I agree with you that the zinc particles do have to truly be in contact with the steel for it to act as a cathode.
Okay, and also the state of California at one time had tried to actually ban zinc as a heavy metal in the industry. And because I think in the mining process, they had also contributed to some lead content. Does Sherwin-Williams take any account to how do we manage and minimize the amount of lead that may be in that mining process?
We actually do. One of the other designations for zinc-rich primer is noted by ASTM 520, the standard for the type of zinc. And what that does, there are 3 types, 1, 2, and 3, and that designates the amount of zinc that is in the dust, the lead content that's in the dust, and the cadmium content that's in the dust. Type 1 allows 0.2% of lead and 0.06% cadmium. Type 2 dust allows 0.01% lead and 0.01% cadmium. Sherwin-Williams only uses type 3 dust, which is the most heavily controlled and the most expensive zinc dust. 97% zinc in the content, 0.002% lead, and 0.001% cadmium. So we use the highest level of zinc dust in all of our primers, regardless of the application.
So why does Sherwin-Williams go to that extra length to make sure that their zinc primers meet those kind of standards?
Quite honestly, it's the right thing to do. I mean, it is the safest for the public. It reduces the amount of lead that could potentially get into water. And we just feel as a company that is the right thing to do. And we commonly lose projects because our zinc will be more expensive, because type 3 dust is more expensive than type 2. It's cost more to manufacture. But we feel as a company that is the ground that we want to stand on, and that's what we go to market with every day.
So now talk a little bit about how are these zinc primers applied? So we touched on it a little bit, whether it's shop or field. What is the difference for people who don't understand what you're talking about when you talk about shop applied, field applied? Are they measured the same way? What does that look like?
For the most part, the zinc primers are spray applied. As Jamie alluded to earlier, they dry very quickly, and that's one thing that shops like about them is the ability to turn steel through a shop. A fabrication shop does not get paid to paint. They get paid for man hours, and the more steel that they can get through a shop, the better. So zincs, whether they're organic formulations or inorganic, the fact that they dry so quickly is very appealing to fabrication shops in new construction. Zinc in small areas can be brush and rolled, but if you have a large surface, 95% of the time you're going to be spray applying that zinc-rich primer.
Would you consider it a dry fall product then when spraying it in the fields? Say in a new tank fabrication, we're just addressing seams and things like that, or in a full containment, if we have to spray it, would you consider it dry fall?
Some products dry quickly enough that they could be considered to have dry fall properties. I wouldn't say that they're a true dry fall, but they do dry very quickly, and they will exhibit some of that dusting characteristics so that after 30 or 40 feet that they won't re-wet onto a substrate below.
What about top coatings? Are they limited to the amount of top coats it can take in time frames?
Inorganic zincs are limited. There's a critical recoat window that you have to wait a certain amount of time. They dry very quickly, but they have to cure the solvent out before you can top coat them. There are some formulations and some manufacturers that have been able to reduce that recoat window, but it's still a significant time gap between when you can coat an inorganic zinc primer with an epoxy top coat. And with inorganic zinc primers, the film, because there's no epoxy resin that's holding it together and isolating the zinc particles from the steel. It's a very porous film. So when you overcoat that with whatever technology you put over an inorganic zinc primer, you have to apply a mist coat of 1.5 to 2 mils to wet out that surface, to displace the air, let that flash off, and then put your intermediate coat of epoxy or whatever you're placing over the top of that inorganic zinc. Organic primers don't have that requirement because they have the epoxy backbone. They can be recoated very quickly. There are formulations now of organic zinc primers that you can spray the zinc on, and at 77 degrees Fahrenheit, they can be recoated in 30 to 45 minutes.
But do they also have a limited recoat window? So do they have a time frame to which they have to be scarified or abraded before they get top coated because of that?
Most of the primers that Sherwin-Williams have about a 1-year recoat window, organic zinc rich primers, before they would have to be abrasively blasted. In the water tank market, when you are sending plate to the field and it could sit out, you always want to clean that. And it's quite common practice to actually go through, and since you have weld seams that need to be addressed anyway, you're going to sweep blast that entire surface. So it really kind of becomes a moot point at that stage what the recoat window is, because you need to address those seams anyway. You've got the nozzle open. You might as well sweep the rest of the plate to make sure that there's no adhesion issues.
And that was one of my next questions. That's one of the things Maguire Iron does is we run things through the paint booth, put them in zinc, and then they might sit outside or, be put on a truck that has to be driven to a site, and then they're going to sit there for a while. So you touched on my next question is what are some of the things that you have to do or make sure you do if it's zinc coming from a factory to a job site so that it doesn't get damaged, or what are some of the best practices to make sure that it stays what it's supposed to stay in the field to hold that paint?
Well, the first thing is you always want to make sure that you have the specified dry film thickness on. If you are light on your dry film thickness, and that allows the peaks of the blast profile to show through as it sits on that truck and it gets rain deposited on it, salts from the road or anything, you've created a corrosion cell on the top, and now you've got a huge problem that you may have to blast that entire plate back to steel. Your holding primer has now completely lost its purpose. At bare minimum, you're going to have to clean that plate, per SP1, or on large structures, you'd pressure wash that to get the salts off of it and the dirt and debris off of it before you proceeded with subsequent coats.
So that leads me to my next question. What is the typical thickness that zinc is applied to make sure that you don't have those issues that you're talking about?
Yeah, probably the lowest that you will see for a zinc primer that's going to stay in place on as part of a specification would be 2 to 2.5 mils, because you're always going to, if you go through a wheel abrader or your hand abrasive blasting, even with the finest media, you're going to have a 1 to 1.5 mil profile. So you've got to have enough zinc film build over top of that to fill the profile in. So 2 mils on the low side is about the lowest you'll see in a specification, and probably up to about 5 mils with some of the organic zincs you can see. The typical range is 2.5 to 4 mils that you see in most specifications.
But you also want to make sure that you don't put too many mils on as well, correct?
That's absolutely correct. Because of how fast zinc-rich primers dry, they are very prone to what's called mud cracking, and that's when you get excessive film build on the top. Flash is over, you still have solvent underneath, and as it tries to escape, it breaks through and creates a mottled film that looks kind of like the skin of an alligator a little bit, and it's weak and ineffective. So that would need to be removed if you had too much film. And it's very common to see mud cracking happen in webs and areas where you have to, an applicator has to spray from a couple of different angles, and they may put 2 mils on one side of the web, and on the flange they'll put 2 mils, but at that where those spray patterns cross, now they've got 4 or 5, or they may put 3 and 3, and now they've got 6, and they mud crack it, and so that needs to be addressed.
How soon does that show up before you start to see it?
You typically see it as the zinc is curing, and your QC should see that when they're checking for dry film.
And the best way to remedy that, if it's found on a job site, would be?
Depending on the size and scope. If you just have a couple of areas, you could come through and power tool clean that off and remove the millage and readdress it. In large scale applications, large square footage, it'd probably be best to abrasively blast it and bring that millage back down.
What is the risk if you miss seeing that mud cracking and you try and put a coating over the top of it?
It'd be similar to coating over unprepared concrete, where you have the latence layer on the top. It's the fines on the top of a concrete. That mud cracking is the same thing. It's an improperly formed film in the zinc coating, and its cohesive strength to itself is very weak. And when you get the stresses of curing from subsequent coats over top of it, it can pull apart on itself, and now you've got a void in your coating or lining system.
What is the adhesion that you typically find between zinc and the steel?
It depends on the product, but you'll see 1,500 to 2,500 psi adhesion strength.
So if an inspector were out and questioning the film thickness and the adhesion and the quality, that's what they would be looking for on a pull-off test then? Is around the 1,000 range, would you say? You
would want to refer to the technical data sheet for whatever product you were using, and what you see as the value that's on that's published by any manufacturer is in optimum conditions in a lab. At perfect millages and everything.
We very rarely ever get optimum conditions hanging 100 feet in the air.
You very rarely see that. So I would say that if you had 65 to 70% of that strength in the field, you would say that could be excellent adhesion between the zinc and the steel.
As an applicator, I've struggled with spraying zinc because of my lack of experience, but I also find that I dry spray it quite a bit. Is that a typical problem you would find within the industry, or is it just something experienced sprayers learn to deal with? And do they what are the surface prep standards if they find they have dry spray, primarily on the interior of a water tank where they have a bowl and it can settle?
Well, the answer is yes and yes. You see that. I mean, dry spray in zincs is a problem. Manufacturers spend a great deal of trying to optimize solvent packages to make sure that doesn't occur. But at some point too, good painting practice come in, and if you know that you're spraying a product that has a tendency to fall out and dry, maybe we throw a tarp down on the bottom to protect the bowl before you get there, so that you don't have that significant buildup.
Would a pole sander across the bottom, if they're dry spray, is that there to be sufficient enough to remove it and sweep it down?
If it's minor dry spray, yes, you commonly screen inorganic or organic zincs to knock that down, and then put your subsequent coats over the top of it.
Now, the last topic we've got, talking about zinc, and I know Jamie's super excited to talk about, and we've touched on it a little bit, is zinc versus cathodic protection. This is another area when we talk about zinc primers where there is some debate in the industry. So I'm going to leave it up to our two experts here to duke it out a little bit. But let's talk about zinc versus cathodic protection. What are the pros and what are the cons? Eric, we're going to start with you.
Well, if zinc primers are applied properly and the zinc particles are allowed to come in contact with the steel, they act as a cathode and they sacrifice themselves to protect the steel. There is significant debate in the industry, though.
Yes, there is. I'm
setting Jamie up. We've been talking about baseball all night. I'm setting the ball up on the tee. There's significant debate in the industry, though, whether or not zincs, when they're suspended in the resin, actually come in contact with that. I'm in the camp that I do see that there is some benefit from zinc primers as a corrosion aid. But I also recognize the stance of the other camp that there can be some issues with that.
Without a doubt, it's a fantastic barrier coating because of the makeup itself and the moisture penetration through the coating. All coatings are permeable to moisture. We know that. It's the rate in which they transfer that makes the difference in the coatings. But in the case of a zinc, being on it is nothing more than a fantastic primer. But what about when they add additional cathodic protection to, say, a water tank, where we know we have cathodes hanging in the water, and yet we have this very expensive barrier protection in there? I don't believe that you need both. And I don't believe that we need to have cathodic protection in a water tank because the technology of our barrier coatings has been able to extend the life of the interior. So I just think that the zinc itself is a good primer. I don't think it really adds as additional cathodic protection. I do think it's a great primer. And I do believe that the cathodic protection that is hung in there by other manufacturers is a separate piece, isn't really useful in the industry.
We get the long pause here.
I
folks.
stumped them.
Long pause. I believe that it's you should choose one or the other. It baffles me, though, to think that you're going to hang anodes in a tank, and the most severe exposure inside of a water tank is the vapor space, the roof rafters. That's where you see your corrosion first and all. It's the hardest to paint. It's the highest away from the ground, and it's not encapsulated in an electrolyte. So it's not seeing truly the benefit of the impressed current cathodic protection. So I think the advancement of using, to your point, ultra high solids products, edge retentive products in those areas to provide increased barrier protection is probably way more of an advantage than cathodic protection.
Thank you to Eric Zimmerman and Jamie Mays for joining us to help us understand the history of zinc-rich primers, how they're made, the different industries they're used in, and how they're applied. Remember, you can always connect with us by going to our website, maguireiron.com. You can ask us a question by sending us an email at info@maguireiron.com, or you can follow or reach out to us on any of our social media platforms. We are on Facebook, Twitter, Instagram, and LinkedIn. Thank you for joining us on the Maguire Iron Podcast.